In this video, I'll describe the basic properties of stars. First, I'll cover brightness and the magnitude system, and the parallax technique for measuring distances. Then I'll describe how astronomers classify stars. There's spectral type, which is related to temperature and color, and luminosity class, which is related to size. Then I'll talk about something called the HR diagram and what it can tell us about stars. Finally, I'll talk about multiple star systems. We'll look at 3 types of binary stars. I'd like you to stare at this image for a few seconds. What can you figure out about a star just by looking at it? In other words, in what ways do stars appear different from each other? You might think there are 3 different ways. In fact, there are only 2. There's color and there's brightness. We see blue stars and red stars, bright stars and faint stars. What we don't see is size. We can't determine the size of a star from an image. I know some stars look big, but these are just the bright stars. Stars are so far away from us that each one should appear as the smallest dot you've ever seen. But the light from each star gets spread out as it passes through the atmosphere and through the different components of a telescope. Brighter stars appear larger because their light gets spread out more. The most commonly used unit for brightness in astronomy is magnitude. It's incredibly stupid because it's backwards. It made sense when the ancient Greeks first came up with it. They just ranked stars according to their brightness. The first set of stars you can see after sunset were first magnitude. Then as the sky gets darker, you see more stars. These are second magnitude, and so on. Claudius Ptolemy took this as far as 6th magnitude. These were the faintest stars you could see. Since it was a ranking system, it made sense for first to be brighter than second, and so on. But later, people started measuring brightness more precisely. So between first and second magnitude, there's 1.5 and 1.05, etc. So they turned the ranking system into a measurement unit. That's what's stupid in my opinion. It's like taking student rankings and turning them into grades. The student with the highest GPA is ranked first. But the student's GPA is not 1. A GPA of 2.0 is clearly better than a GPA of 1.0. Oh well, today we're stuck with this system. All you have to remember is that smaller magnitude means brighter. The apparent magnitudes of a bunch of objects are shown on this chart. There are a couple of stars that have negative magnitudes. Mars, Jupiter, and Venus can be even brighter. And of course, the brightest celestial object is the Sun. The full moon is a distant second. Apparent magnitude, as the name suggests, tells you how bright an object appears to us, not how bright it really is. To figure out how bright a star really is, we have to first figure out how far away it is. One of the most reliable ways to measure the distance to a star is a technique called parallax. It's quite simple. Do something for me. Hold one finger out in front of you, close one eye, and line the finger up with some object in the room you're in. Now switch eyes. Open that eye and close the other eye. Your finger should appear to move when you do this. This is parallax. It's the apparent shift of an object due to a change in your perspective. You look at an object from 2 different vantage points, and it appears to shift relative to background objects. The distance between the 2 vantage points is called the baseline. You might remember that term from interferometry. We have the 10 radio telescopes that make up the Very Long Baseline Array, for instance. The bigger the baseline, the bigger the parallax shift. When I ask students what the biggest baseline is that we have access to, most of them say it's the diameter of the Earth. In other words, you could have 2 people on opposite sides of the Earth take pictures of the same stars. It turns out that we have access to a much bigger baseline, and it doesn't even require a second observer in Asia or Australia. That's because we go halfway in our orbit around the Sun every 6 months. That's a baseline of around 186 million miles. We can just take a picture tonight and another one 6 months from now. At time A, the red star appears between these two stars. 6 months later, at time B, the red star appears between these two stars. The white stars don't appear to shift because they're further. The further a star is from us, the smaller its parallax shift. Using this technique, astronomers have measured the distances to hundreds of thousands of stars. There's one thing that makes this a bit more complicated. Stars really do move too. All the stars we can see are orbiting the center of the galaxy, but they can move at different speeds and in slightly different directions. The actual motion of a star is called proper motion. The star with the largest known proper motion is Barnard's star. It was here in 1985. By 1995 it had moved to here, and by 2005 it had moved to here. So it moved from here in 1985 down to here in 2005. So let's say you take a picture tonight and another one 6 months from now, and one of the stars appears to have moved. How do you know if it was parallax or proper motion? In other words, how can you tell if the shift was just because we were looking at it from opposite sides of our orbit around the sun, or if the star really moved? All you have to do is wait another 6 months and take another look. If you look at a star tonight and then a year from now, you should see no parallax shift. If all it does is keep going back and forth every 6 months, that's just parallax. If, on the other hand, it keeps going in the same direction year after year, that's proper motion. Parallaxes and proper motions of even the closest stars are too small to detect with the naked eye within one lifetime. But over timescales of tens of thousands of years, proper motion will cause stars to move noticeably. This is how the Big Dipper looks today. This is how it probably looked 50,000 years ago, and this is how it's expected to look 50,000 years from now. Once you measure the distance to a star, you can figure out how bright it really is. This is described by its absolute magnitude. Here are apparent and absolute magnitudes for a few stars. The Sun is obviously the brightest star in the sky, by far. It has an apparent magnitude of negative 26.7. But the Sun is not by any means the brightest star in our galaxy. As stars go, it's actually below average. If I gave the Sun a grade, it would be a C-. The Sun's absolute magnitude is 4.8. The second brightest star in the sky, or the brightest star in the night sky, is Sirius. It has an apparent magnitude of negative 1.5. Its absolute magnitude is 1.4. So if it were as close to us as the Sun is, it would actually look much brighter than the Sun. It is 25.4 times as luminous as the Sun. The more luminous a star is, the smaller its absolute magnitude, because remember, magnitude is a backward scale. Let's skip to Proxima Centauri. This is the closest star to the solar system. In other words, it's the second closest star to us, after the Sun. It's incredibly faint. Its apparent magnitude is 11.1. It's not even remotely visible to the naked eye. We can only see down to 6th magnitude, even on the darkest, clearest night. As expected, Proxima Centauri has an extremely large absolute magnitude, 15.5. This star is 0.002 times as luminous as the Sun. Then there's Betelgeuse, or Betelgeuse. It's a bright red star in Orion. It's got a small apparent magnitude, which means it looks bright. Its absolute magnitude is much smaller, which means it's extremely luminous. Finally, I included here a star called Cygnus OB2-8A. It's not bright. It's not visible to the naked eye. That's why it doesn't have a real name like Sirius or Betelgeuse. It's just identified as some star in the constellation Cygnus. But look at its absolute magnitude. It's negative 7.2. This star is 650,000 times as luminous as the Sun. It's one of the most luminous stars ever discovered. Spectra give us much more information than images do. They tell us something about chemical composition. Just above the photospheres of most stars, there's a cooler layer where atoms absorb light. Some stars show hydrogen absorption, some show calcium absorption, etc. The person who has contributed the most to spectral classification was Annie Jump-Cannon. She could do this better and faster than anyone else. After classifying hundreds of thousands of stars at Harvard over a period of around 50 years, she was finally given the title of astronomer at the age of 75. Until then, she and the other women who contributed so much to astronomy were referred to as computers. A computer was a person back then, not a thing. By Annie Jump-Cannon's time, there were already several different spectral classification schemes. Initially, they were based on whether or not a star had hydrogen lines and how strong they were. And then people took these and arranged them according to temperature. So we've ended up with a ridiculous system. From hottest to coolest, the spectral types of stars are O, B, A, F, G, K, M. It appears to make no sense whatsoever. The subtypes are numbered. So an O2 is cooler than an O1 and hotter than an O3. If you look at this figure, you might be able to see a gradient with the O stars appearing brightest in the blue part and the M stars appearing brightest in the red part. Now the Sun is classified as G2. So its spectrum would be between the G0 and the G5, shown here. This figure shows which atoms or molecules are seen in stars of different spectral types. For instance, A stars have strong hydrogen lines. You don't have to memorize any of this. One thing astronomers are good at is coming up with clever ways to remember stupid things. The one mnemonic device you'll find in every astronomy textbook is O-B-A, fine, girl or guy, kiss me. You will need to remember O-B-A-F-G-K-M. This should help. If you don't like it, here's another one. Oh boy, an F grade really kills me. Or you can come up with your own. Beyond M are the failed stars, which are known as brown dwarfs. Their cores are not hot enough to fuse hydrogen. They're less massive than stars, but more massive than planets. There are a lot of brown dwarfs out there. They're just very hard to see because they're not at all luminous. Here's the Orion Nebula in visible light. None of the stars here we can see are brown dwarfs. That's the image shown on the left. In the infrared image on the right, most of the faintest stars are brown dwarfs. Due to the low temperatures, brown dwarfs are best studied in the infrared. Here is a map of the stars closest to us. The brown dwarfs are circled. The ones in the blue circles were discovered by a different team than the ones in the red circles. The stars that appear red are shown brighter than normal. Notice that most of the stars in the image are fainter than the Sun. I'd mentioned earlier that the Sun is below average. If you arrange the stars from highest luminosity to lowest luminosity, the Sun would be on the low luminosity side. But if you focus not on where each star is in terms of luminosity, but how many stars there are at each location, you would see that most of them are on the low luminosity end. You would have a couple of luminous stars and a whole bunch of low luminosity stars. The same would be true if you arrange the stars according to temperature. The Sun would be on the cooler side, but so would most of the other stars. There would just be a couple of hot stars and a whole bunch of cool stars. To picture this, assume each star is a person. You're the Sun. Don't read too much into this or take this too personally. It's just a metaphor. As the Sun, you're not the brightest student in the class. You're also not the hottest student in the class. You're below average in just about every way. You just don't stand out. Even physically, you're small. You're about 5 feet tall and weigh less than 100 pounds. But here's the thing. Most of the other students are like you, or even duller, smaller, and more plain looking. There's one kid in class that's super bright, just physically massive and super hot. This kid's a giant, 7 feet tall and 400 pounds. It's also the only person that always gets straight A's. And then there are a couple of other kids that are bigger, taller, brighter, and hotter than you are. But most of the class is tiny and dull. So when your relatives ask you why you're only getting a C minus in class, you say, hey, most students are doing far worse than me. There's just one kid with an A and a couple with B's. Most are failing. In this class, a C minus is not bad at all. In other words, you're doing fine on a percentile basis. Your score in the class might be a 70%, but you're in the 90th percentile. A couple of astronomers named Hertzsprung and Russell independently noticed that if you plot the luminosities of stars against their temperatures, most of them lie on a diagonal line from the top left to the bottom right. This is called the main sequence. It turns out that these are the normal living stars which fuse hydrogen. The Sun, being slightly below average, is slightly below center and to the right. The hot, blue, massive, luminous stars are at the top left. The cool, red, tiny, dull stars are at the bottom right. There are many more stars at the bottom than at the top. You might remember that if two stars have the same size but different temperatures, the hotter one should be more luminous. It so happens that a blue main sequence star is also bigger than the Sun. But even if it were the same size, it would be much more luminous because it's hotter. That means the stars at the top right must be huge. The only way a red star could be as luminous as a blue star is if the red star is way bigger. The stars at the top right of the HR diagram are up to 1,000 times larger than the Sun. These are called red supergiants. At the other extreme are stars that have very, very low luminosity despite being hot. That means they have to be tiny. These are about 100 times smaller than the Sun and only about the size of the Earth. These are called white dwarfs. The size of a star is described by its luminosity class. Roman numerals 1 and 2 are supergiants. 3 and 4 are giants. The main sequence stars are 5. They're also sometimes referred to as dwarfs, which is terribly confusing because they're not the same as white dwarfs. White dwarfs are even smaller, at Roman numeral 7. Between main sequence stars and white dwarfs is a category called subdwarfs, which I'm not going to get into. You can look it up if you want, but you don't have to know anything about these for this course. So the complete classification of a star includes spectral type and luminosity class. The spectral type tells you temperature, while the luminosity class tells you about size. The Sun is a G2 Roman numeral 5, which means it's relatively cool and small. Sirius is a bit hotter. As an A main sequence star, it's also slightly larger than the Sun. Proxima Centauri is cooler than the Sun. As an M main sequence star, it's also smaller than the Sun. Betelgeuse is also cooler than the Sun, but it's a supergiant. In this case, its size more than compensates for its low temperature, and so it's extremely luminous. In summary, the upper main sequence stars at the top left of the HR diagram are massive, blue, luminous, and large, but not very common. The lower main sequence stars at the bottom right of the HR diagram are red, small, and have low mass and low luminosity. There are also more of them. And there's one more thing. The low mass stars live much longer. The life expectancy of the Sun is 10 billion years. That's not bad at all. It's currently 4.5 billion years old, but still has more than half of its life left. The most massive stars live for only a few million years. The least massive stars live for hundreds of billions of years. In our scenario where we compared stars to students, that would be like the hot, bright, 7-foot, 400-pound student, living for just a day or two, while the dull, tiny, 4-foot, 10, 80-pound students living for thousands of years. As the sun, you can get together with your tiny, dull friends hundreds of years from now and reminisce about the early days. You could say, remember that crazy, hot, crazy, bright, giant kid? That kid got all the attention for a day, haha, and then he disappeared. And we are still here. Some of the red supergiants are so big that if the sun were replaced by one of them, we would be inside the star. Here is one of the largest stars known. Here is a white dwarf, the faint star here. It's Sirius B, the companion of the brightest star in the night sky. Although the white dwarf looks really faint in visible light, it actually appears brighter than Sirius A in the X-ray image on the right. That's because the white dwarf is much hotter than its main sequence companion. The majority of stars have companions. This includes our nearest neighbors, the Alpha Centauri system. The star that appears really bright to the naked eye is actually two stars, Alpha Centauri A and Alpha Centauri B. Here's the combined light from both of them, and here's the zoomed in image of that part of the larger image. A distant, faint third star was discovered later. It was initially called Alpha Centauri C, but was renamed Proxima Centauri because it comes closest to us. Here is a close-up of Proxima Centauri. Just by looking at this image, there'd be no way to know that this star is closer to us than all of these other stars, which happen to lie in the background. Proxima Centauri takes around 550,000 years to go around Alpha Centauri A and B. If it weren't so close to us, we wouldn't have noticed its proper motion. If you can see two stars orbiting each other, that's called a visual binary. Those are actually quite rare. Either the two stars are so close together that it looks like just one star, like Alpha Centauri A and B over here, or they're so far apart that we don't notice them moving around each other. Spectroscopic binaries are much more common than visual binaries. You might only see one star, but each absorption line in the star's spectrum gets split into two and combines into one again. What's happening is that you're seeing the combined spectra of the two stars. When one star is moving towards us, its absorption lines are blue shifted. At that time, the other star is moving away from us, and so the same absorption lines are red shifted. When the stars are moving sideways relative to us, the lines have no Doppler shift. So in this image, star A is moving towards us, and star B is moving away from us, and so star A is blue shifted, star B is red shifted. The opposite is happening down here at the bottom. Here and here, the stars are moving sideways with respect to us, and so we see no Doppler shift. If a binary star system is nearly edge-on, we might see the two stars eclipse each other. In an image, we might only see one star, but if we keep monitoring the brightness of the star over time, we'll see that it dips at regular intervals. Most of the time, the light curve is flat, because we're seeing light from both the stars. When one star passes in front of the other one, it blocks all or part of the light from the background star. We always get a bigger dip when the cooler star eclipses the hotter star. At position 2, the blue star is eclipsed by the red star, and so we see a big dip. When the hotter star eclipses the cooler star, which happens at position 4, we get a small dip. It actually doesn't matter which star is bigger. That's because it's the same size region that gets blocked each time. Here the red star happens to be bigger. When the blue star is in the back, all of the blue star gets blocked. When the blue star is in front, it blocks the region on the red star that's the same size as the blue star. In both cases, the size of the region that's blocked is the same. It's the size of the smaller star. So what matters is how much light is coming out of that region. You might remember from chapter 5 that a hot star is more luminous than a cool star of the same size. Here the two stars are not the same size, but the region that's eclipsed is the same size. That's what matters. The actual sizes of the stars don't matter. Just remember this: we always get a bigger dip when the hotter star is in the back. Another nice thing about eclipsing binaries is that they allow us to determine how big the two stars are. If you look at how long it takes for an eclipse to begin or to end, which is from time 1 to time 2, or from time 3 to time 4 in this figure, you can measure the size of the smaller star. You can measure the size of the larger star by tracking how long it takes the small star to go across it. Here that would be from time 1 to time 3, or from time 2 to time 4. Binary stars are useful to astronomers because they allow us to measure masses. The two stars orbit the center of mass. The more massive star has a smaller orbit than the less massive star. If you know the orbital period and distance, you can use Newton's version of Kepler's third law to get the masses of the stars. This is the only direct way to measure masses in astronomy. We can only measure the mass of something if it has something else orbiting it.